Hello, Chem 2, and welcome to the last video of the spring 2020 season. We're going to be focusing on the last two sections of Chapter 13. That is the Ka equilibrium and Kb equilibrium. So let's get started. This chapter, we're only going to cover 1 through 5. 6 and 7 we're going to deal with in AP, but we're going to look at 4 and 5 today. First one we're going to do is the acid side and Ka and how to use Ka. This is all the objectives for everything. We're going to look at pH compared to the Ka compared to the hydrogen ion concentration, Kb to the OH concentration, the Ka and the Kb, how they compare to one another. So a lot of stuff to be covered. And again, this might be a little bit of a longer video. So if you need to take a break in the middle between the 13-4 and the 13-5, feel free to take a break. The joy of being able to pause me whenever you feel like it. So let's get started. So section 13.4 is all about weak acids and their equilibrium constant, the Ka value. So weak acids, they are compounds that will act in an equilibrium with water and form the hydronium ion and some other anion. So you either have a molecule that has a ionizable hydrogen ion, like in this case, the nitrous acid can just simply lose one, or sometimes the conjugate acid of a base, a conjugate acid of a base can also act like a acid. Look at that ammonium ion. The ammonium ion can interact with the water to form hydronium and some ammonia. Ammonium is the conjugate base, the conjugate acid of the base, which is ammonia. So as long as there's a hydrogen that can be transferred to the water, you got yourself a weak acid. Because we're talking about weak acids, we have the Kas. And we're going to use this generic concept of Ka being the hydrogen or hydronium ion concentration times the anion divided by the acid, because this water is liquid. So we ignore that. The Ka is going to be very, very consistent. We're going to constantly see the same thing over and over again. And one of the things that's really, really great about this last section of equilibrium is the fact that there is going to be a much simpler approach to the equilibrium expression. Hydrogen times the anion divided by the base, or the hydrogen times the conjugate base divided by the acid. You're always going to have the same basic format. And we already know. You may see values given to you as Kas, as a pKa. P is just a function. It's a negative log of something. It's just a P. P is a way to express negative log of. So if you had a pKa was given to you, that would be the negative log of the Ka. So again, to go backwards, you would take 10 to the negative pKa to get the Ka. Does that make sense? Maybe not. Okay. So here's some various Kas and Kbs. Sulfurous acid, that's the acid, that's the base. Notice that the Ka is kind of large and the Kb is really, really small. Hydrogen sulfate, Ka is kind of big, but the Kb for its conjugate base is pretty small, and vice versa. They work together. All these acids have conjugate bases that are pretty small. Same thing on the other side. Some Kas on the base side. All these guys are bases. They have Kas that are very small, but the Kbs are relatively big. So let's talk about how to use this. How to use Ka and Kb. Let's look at Ka first. So let's look at an example. Suppose I make a solution of nitrous acid that is 0.495 molar. Simply put, I'm going to measure out 0.495 moles of nitrous acid and put it into a total volume of 1 liter of solution. And then I put a pH probe in there and I calculate that the pH is 2.34. I want to know what the Ka is. Now, if we were in class under normal circumstances, this would be a great springboard, because this is the lab we were going to do. We were going to make different solutions of acid and then measure their pHs and see what the relationship is between the concentration of the acid and the Ka. And the reality is Ka should stay constant. Unless you change the temperature, the Ka is going to be constant. So let's figure out what the Ka is for this. So we have a 0.0495 molar solution of nitrous acid. This is nitrous acid breaking down into hydrogens and the nitrite ion. So the Ka, so the numbers you have are the the nitrous acid is 0.095, and from a perspective of I added 0.095 moles of the acid to a total of 1 liter, I'm starting off with no hydrogen and no nitrate. So the right-hand side has to get the pluses because they're zeros. We got to get them to have some value. And the left-hand side has to be the negative. So you go with your numbers, and we have variables. Okay, we need to figure out what the hydronium ion concentration is going to be 10 to the negative of the pH. So I can fill that in. Okay, the hydronium or the hydrogen ion concentration is 10 to the negative of the pH. They gave me what the pH was. The pH was 2.34. So what that's telling me is my hydronium concentration is 4.6 times 10 to the negative third. That would be that number there. So both of these are 4.6 times 10 to the negative third. Okay, both of those are 4.6 times 10 to the negative third. That's what we just figured out X was. Which means if we're going to subtract that from the 0.095, we get 0.0449. So now we have the concentrations of all three components. Since we have the concentrations of all three components at equilibrium, we can then do our Ka. Hydrogen times nitrite divided by nitrous acid, put the numbers in, get a number. This acid happens to have a Ka of 4.7 times 10 to the negative fourth. You can determine the Ka of a solution if you know the concentration of the acid you added and you are able to measure the pH. And again, this is the lab we would have done in class. Let's look at some other possible calculations. Now, in this situation, you are given the pH. But what if you are asked to calculate the pH or to calculate the hydrogen ion concentration in a weak acid? You'd have to know the Ka value. And as they say here, the value of the Ka is usually not known more than plus or minus 5%. So sometimes you're going to have to use some numbers and do some permutations to find out what the concentrations are. So this is expression. X is the concentration of hydronium, which we know is also the concentration of the anion, divided by the original concentration of the weak acid minus whatever that X was. So if the comparison of X divided by A is less than 5%, this is called the 5% rule. If the amount of acid that you have, the number of hydrogen ions you have compared to the original acid is less than 5%, we can make an assumption that X is negligible and just go ahead and roll with it. Okay? It makes the calculation so much easier. So we have to figure out what the ratio is between the hydronium ion and the acid. And you're going to see in a little bit, we're going to take some liberties of assuming it's less than 5% and then checking to confirm that it really is. Okay. Another thing that's going to show up on the OWL is a calculation of ionization. Now, it's a little different. Ionization, if you think about the way that an acid ionizes, if you take the original acid, Hb, in its original concentration, and you want to know what percentage of the original concentration ionized, you would take the amount of hydrogen ion that was created and divide it by the original amount of the acid. Not the amount of acid at equilibrium, but the original amount of acid. That's why this subscript 0 at time 0 before it reached equilibrium. And then we talk about the 5% rule. If the hydrogen ion is greater than 5%, then you got to use quadratic formula or successive approximations to get there. We'll use quadratic formula if we have to get there. So let's try one. It says calculate the hydrogen ion concentration of a solution of nitrous acid, which Ka is 6.0 times 10 to the negative fourth. Now I'm going to tell you from experience that in the 10 to the negative fourth, 10 to the negative fifth, and smaller, that's where you start being able to consider using the 5% rule. When your numbers are bigger, 10 to the negative third, 10 to the negative second, 10 to the negative first, it's not even worth it. Go straight to quadratic formula. But in this 10 to the negative fourth, 10 to the negative fifth range is when you can consider trying to use the 5% rule and trying to assume that it is an insignificant amount, and then going ahead and finding out whether it is or is not. We're going to check this one out. So we know our amounts of the acid. We start off with 0.1. We know our Ka. We know that the hydrogen ion we're looking for is the hydrogen ion at equilibrium. And what we're going to turn out doing is plugging the numbers into a Ka expression and finding out what the concentration is. I apologize for the noise. I think I told you in a previous video, I am upstairs in my quote-unquote studio. I have the window open because it's nice outside, but I am very, very close to the road, so you're going to hear cars go by. I just heard a motorcycle go buzzing by. Okay, let's look at this. So let's assume that X is very, very small. We're going to assume that X is very, very small, and we're going to assume that we can ignore it. And then we're going to, when we're done, calculate the percent ionization and see whether or not it really is less than 5%. If not, we're going to have to solve for X, go back and do it again using quadratic equation. As I've said, as far as Ka's go, if you are in that 10 to the negative fourth, 10 to the negative fifth, and smaller range, you can almost always try to use this assumption. If you're 10 to the negative third, 10 to the negative second, 10 to the negative first, forget it, just go straight to quadratic. You're going to waste your time. 10 to the negative fourth, 10 to the negative fifth, in that range, you're going to do double the work. You're going to do it the quickie way, and then maybe sometimes find out you have to do it the long way. So let's look at this. Here's your equilibrium expression. Hydronium or hydrogen times nitrite divided by the nitrous acid is equal to those numbers. And then what we're going to do is we're going to assume that X is really, really small compared to 0.1. So we're going to ignore it. So we're going to cross that out. So it just becomes X times X over 0.1, or X squared over 0.1. And we're going to do the math. The math is easy. 6.0 times 10 to the negative fourth times 0.1 equals X squared. And we're going to solve for X and find out that to be 0.0077. That's my concentration of hydrogen of this solution. Let's see whether we're allowed to use the assumption. So we're going to check our ionization. We're going to take amount of hydrogen ion, 0.007, and divide it by the concentration of the acid, which is 0.1 times 100%. And lo and behold, we get a value of 7.7%. Since our number is greater than 5%, we're not allowed to use the assumption, and we have to go the full route of doing the full process of determining the concentration using the quadratic formula. So if I use the quadratic formula and do my cross multiplying, I get this. Put it into the quadratic equation, solve for two answers. One of them works because you can't have a negative concentration. So the concentration of the hydronium ion is 0.0074. Not a significant difference, but a more accurate difference considering that we had greater than a 5% ionization. So we have to do, since it's 7.4%, we have to do it fully using the quadratic formula to get the most accurate possible answer. Now, let's be honest. You can always use quadratic formula. If you're comfortable using the quadratic formula, it'll work every time, and you don't have to think about this whole 5% rule. The 5% rule is here just to make the calculations go a little bit quicker under some circumstances. What about polyprotic acids? Well, polyprotic acids mean that they have more than one proton, like phosphoric acid, H3PO4. It has 3 different protons. And for each one of the protons that are being stripped off, they're going to have a different Ka value. Every single one of the protons is going to have a greater Ka value. But what you should know is the Ka for the first proton is going to be bigger than the second one, is going to be bigger than the third. As you strip more and more protons off, it's going to be harder and harder to take protons off. So it's going to hold on a lot tighter. So for instance, here's diprotic acid of oxalic acid. It's got 2 protons. First proton has a Ka of 10 to the negative second. The second proton, 10 to the negative fifth. Significant differences and very different, but the second one is always going to be less than the first one, and third one, if there is one, is going to be less than the second one. Here's a triprotic acid, is phosphoric acid like I mentioned before. Phosphoric acid, first one, 10 to the negative third. Pretty strong. Second proton, 10 to the negative eighth. Very weak. Third proton, 10 to the negative 13. Super weak. Okay, so 3 protons, 3 different Kas, 3 different values. And here's a couple more that showed you the numbers for those, but also gave you carbonic acid and sulfurous acid to show you the trend. Okay, so that's the acid side. Let's talk about the bases. On the base side, or the KB side, it's going to be very, very similar, but our reactions are going to be ones where the base is going to interact with the water to make hydroxides. So when our ammonia reacts with the water to make ammonium and hydroxide, that makes ammonia a base. You can also happen if you just have a straight up anion, which happens to be the conjugate base of a weak acid. Okay, so a conjugate base of a weak acid. Fluoride is a conjugate base of a weak acid. When it interacts with water, it's going to make hydrofluoric acid. It's a weak acid, and it's going to make some hydroxide. The fact that fluoride interacts with water to make hydroxide makes it a base. And since it is weak, it's going to be a weak base. There's a strong similarity between ammonium and fluoride. They both accept protons, which is they do, and they both act, when you think in terms of a Bronsted-Lowry acid, they both act as Bronsted-Lowry acids on the proton to form the hydroxide. So very, very similar. We have a KB here. Now let's notice the similarities between the two, okay, between what we did before. When we had Ka, it was the hydronium times the ion divided by the acid. Well, this time it's hydroxide times the resulting cation divided by the base. Okay, it's going to be hydroxide times the resulting cation, the one that's made as the base receives the proton. It's going to be the conjugate acid divided by the base. Hydroxide times the conjugate acid divided by the base. Okay, so we have the same format, same thing, always ones, makes life a little bit easier. It's just sometimes a little difficult to write the equations. When writing these equations, make sure you take your base and interact it with water and see how that hydrogen is received by the base from the water. The stronger the stronger the base, the higher the value of the Kb is going to be. The same way, the stronger the acid, the higher the value of the Ka. And yes, we still have the same idea of the pK. You can p anything. P means negative log of. So how do we go about calculating the hydroxide in a water solution of a weak base? Well, it's going to go through the same process we did on the previous example, where you had to calculate the hydrogen ion. And sometimes the Kb can be found, be used to find the hydroxide. Okay, so you're going to do the hydrogen and then sometimes the hydroxide, or you're going to do the hydroxide and then use the hydrogen to get the pH. Let's try this. It says, what is the hydroxide ion concentration of the pH of a 0.3124 molar solution of ammonia? And they gave you the ammonia's Kb to be 1.8 times 10 to the negative fifth. Well, there's my reaction. Ammonium times plus the water, giving me ammonium plus the hydroxide. So that's my equation. I know that I'm starting off with a concentration of 0.3124 molar of ammonia. So I 0.3124 molar of ammonia and none of the other two. Feeling the trend of being very similar to the other one. I know that side is going to be the x because I got to get up to a number and it starts off with 0. I know this side is going to be the minus, which means this side is the x is 0 plus x is x, and this side 0.3124 minus x is my amount. I'm going to go ahead and put that number into, assume that it is 0 is small. We're going to find out in a second. And put those numbers into my expression. So it'd be x times x divided by 0.3124 is equal to 1.8 times 10 to the negative fifth. I'm going to put those numbers in the equilibrium spot into my equation. So x times x divided by 0.2314 is equal to 1.8 times 10 to the negative fifth. And I told you that 10 to the negative fifth is like that cutoff point. You know, you start being able to more consistently use the assumption rule. We're going to have a chance to check to see whether it is good enough. Solve for x by cross multiplying, take the square root of both sides, and I get that the concentration of my hydroxide, the x value, is 0.00237. Now I said you could always use the quadratic formula because that'll always work, but sometimes it might be kind of clunky. If we were to use the quadratic formula in this, I can tell you that the answer you would have gotten was 0.00236. Not very much off, only off to the third decimal place, and not bad considering my my KB has only 2 sig figs. So let's check to see whether we were allowed to use that 5% rule, okay? So let's go do the math. 0.00237 divided by 0.3124 times 100, I got 0.7%. Absolutely, I can use the 5% rule. I don't have to go back and use the quadratic formula. I showed you what the numbers were to make sure, but you do not have to use the quadratic formula. So we're good to go. So hydroxide concentration. Okay, the hydroxide concentration is 0.00237. That means the POH, which is the negative log of the hydroxide ion concentration, is 2.625. You see, I gave you what it was if we went through the whole problem with using it with the quadratic formula. Okay, so that's my POH. And then it asks you for the pH. Well, pH plus POH is 14. So 14 minus 2.625 is 11.375. Again, 11.372 if I use a quadratic formula. And that is definitely basic. So this is a basic solution to begin with. Should be pretty obvious. Okay. Last thing of the video and last thing of all of these endeavors is to connect Ka and Kb. Now, here's the trick. If I have a relationship, I have a conjugate acid-base pair, and I were to compare their Ka of the acid and the Kb for the base, the Ka for the acid and the Kb for the base. Notice what you have here in the first equation. HB is an acid. When it dissociates or ionizes, it becomes hydrogen plus the B. The B is the conjugate base of the HB. And if I were to react that with water, I would get HB and OH. The relationship between the two is that the Ka for HB times the Kb for B is going to be the same as Kw 1.0 times 10 to the negative 14th. So essentially, Ka times Kb for a conjugate acid-base pair, the Ka times the Kb for a conjugate acid-base pair is going to be equal to the Kw, or 1.0 times 10 to the negative 14th. And with that, they talk very briefly about them being inversely related. As Ka gets bigger, Kb gets smaller, and vice versa. Big Kas mean small Kbs, and vice versa. And here's some example values to show you the relationship. We saw these on a previous slide also. Okay? And with that, we are done. So congratulations, you have survived the craziness that is distance learning and the COVID and all that stuff. You guys know that the homework is going to be there for this chapter. You have the optional OWL, you have the required OWL, and you have the chapter 13 test. Do the best job you can, do as much as you can up until the 11th of June. With that being said, one last time, be safe, be healthy, practice your social distancing, I sure would like to see you guys in the very near future. Maybe we can start the next school year somewhat normal. Take care of yourselves, and until the next video, which will be in AP or beyond, sig figs really do matter. Toodles.